problem 44, chapter 15, Giancoli 6 edition. So we have a real heat engine working between heat reservoirs at two different temperatures. And let's write down these two different temperatures. The hot one is 970 Kelvin, and the cold one, I'll call it low temperature, is 650 Kelvin. Okay, and this engine produces a certain amount of work per cycle. Let's write down this amount of work. This amount of work is 550 joules. So it produces this amount of work per cycle for a heat input of a bigger amount. This heat input is the Q that we get from the hot reservoir, which is 2200 joules. But we know we have losses involved, and we have a QL. Not all of this QH, not all of this heat from the hot reservoir will be used for the work. Okay, now comes some questions. First, we want to compare the efficiency of this real engine. So I'll call it the efficiency of the real engine. We want to compare that with the efficiency of an ideal engine. The ideal one is for the Carnot engine. So this is question A. All right, so this we know how to solve. We have to find each one of these efficiencies and then just look at this ratio. So how do we find the efficiency for the real one? The work divided by the amount of input heat, the one that comes from the hot reservoir. So we find this number. And for the ideal, for the Carnot engine, how we find is 1 minus TL divided by TH, or equivalent TH minus TL divided by TH. Okay? Remember, for the ideal, we deal with the temperatures, while for the real, we deal with the heats and the work. So the ideal doesn't exist in nature. It's the maximum possible efficiency that we could get. Okay, so this is it. That's how we're going to find this ratio here. Let's go for question B. Question B is calculate the total entropy change of the universe per cycle of this real engine. Okay, so the total change in entropy will depend on the change in entropy from the hot reservoir and the change in entropy for the cold reservoir. The hot one loses Q and the cold one receives Q. So the hot one loses, so that's why I put here minus QH, and it loses at a constant temperature, which is that temperature for that hot reservoir. So this is such a big reservoir that the temperature does not change. And what does the cold one do? It receives KL, right, at a constant temperature TL. And that's it. That's how we are going to obtain the total change, the total entropy change of the universe for this real engine. How would we find now for the ideal engine? For the ideal engine, we have to use the same thing. Now is again delta S, thinking about the hot and the cold reservoir. So the delta S for the hot, the delta S for the input, plus the delta S for the cold, the delta S for the output. Again, the same equation, all right? So the hot will lose heat and the cold will receive heat. The question now is, what are we going to put for the hot and what are we going to put for the cold? Let's just do this problem symbolically, okay? What do we know is that efficiency is KH minus KL, this is the work, divided by KH. This is a general expression valid for any engine, ideal or real. Okay? Now, in the case of the ideal, I also know that, so for the ideal one, I also know that the efficiency is the hot minus the temperature for the low divided by the temperature for the hot. Okay, so from here, what I'm going to do is try to find the QL. So how am I going to find this QL? The QL that I want to find is obtained like this. This E is equal to 1, no? QH divided by QH minus QL divided by QH. This means then that QL divided by QH, okay, is equal to 1 minus the efficiency. All right, so then what I conclude is that this QL is equal to QH 1 minus the efficiency. And which efficiency are we talking about here? The efficiency from Carnot, the efficiency for this ideal machine. So then I can say that this QL is QH 1 minus this ideal this efficiency for the ideal machine, which I can write as 1 minus TL divided by TH. So this is what I'm going to put here. So here I'm going to say 1 minus TL divided by TH. All right, so then I can say that this QL is equal to QH 1 minus 1 plus TL over TH. So these ones cancel, and I finally found that QL is equal to QH multiplied by TL divided by TH. All right, so I found an expression for the QL that I'll have to put back into this equation here. So let me write this equation again down below. What I want to find is the change in entropy for this perfect Carnot engine, and this will be minus the heat that we lose at the constant temperature for the hot reservoir, plus the heat that the cold reservoir receives at the constant temperature. All right, so I'm going to write all this symbolically, and what I'm going to substitute here is this QL that we just found. This QL is QH TL divided by TH. And here I also have this TL, so let me put it here. So I see that this TL cancels, and now I found that the change in entropy is minus QH divided by TH plus QH divided by TH. Aha, this is 0. This is 0 because the Carnot engine is an ideal engine. It's an reversible engine, and in reversible systems there is no change in entropy. Now, entropy is a measure of how irreversible the system is. Now, entropy is a way to tell us that there is this error in time, that there is a preferential direction in all of these processes. So the Carnot engine is ideal, is reversible. That's why the entropy should be 0, and we have just proved it now with this problem.